Hello everyone, I am glad to share my recent research with you here. In this brief presentation, I will talk about the evaluation and improvement of interpretability for the part prototype networks. Part prototype networks are recently emerged deep self-explainable models for image classification, which define multiple trainable prototypes that represent specific object parts and make predictions from them. These networks achieve comparable accuracy to non-interpretable counterparts. However, recent works find that do not have adequately credible interpretability due to two phenomena. The first phenomenon is inconsistency, which refers to that a prototype may mistakenly correspond to different object parts in different images. And the second phenomenon is instability, meaning that a prototype may mistakenly correspond to different object parts in the original image and the slightly perturbed image. According to these two phenomena, our work proposes a benchmark to evaluate the interpretability of part prototype networks with two evaluation metrics, which are consistency score and stability score. These two metrics are calculated using the annotations in the dataset. The consistency score evaluates whether the prototypes are mapped to the same object part across different images. The stability score evaluates whether the corresponding object parts of prototypes keep unchanged on the perturbed images. This figure demonstrates two examples for determination of consistency and stability. After establishing the interpretability benchmark, our work further proposes an elaborated part prototype network with two modules named SDFA module and SA module. The SDFA module aligns the spatial similarity structure of deep feature maps with that of the shallow feature maps. To mitigate the problem that the matching of each prototype with its corresponding object part is disturbed by other categories, SA module aggregates the activation values of prototypes only into their allocated categories. Besides, our work adopts several simple but effective modifications on the vanilla proto-PNet, and the total loss function is shown as below. The overall framework of our model is demonstrated in this figure. This figure demonstrates the proposed benchmark on the CUB dataset. Some important conclusions can be drawn from the benchmark. First, the vanilla proto-PNet has insufficient interpretability. Second, the accuracy of part prototype networks correlates positively with their consistency and stability scores overall. We conduct two additional experiments to verify this. As shown in Figure A, the test accuracy on images from each class correlates positively with its ratio of consistent prototypes. Figure B shows that the consistency score increases along with the training process of proto-PNet. Our work integrates the SDFA and SA modules into our revised proto-PNet, and the consistency score, stability score, and accuracy of final model are significantly superior to current part prototype networks on the CUB dataset. We also provide many visualization results of our proposed model for better understanding of it. That is all. Thanks for listening.